Well, hope you did well in your test today. This is Algebra 2, and this is going to be our last chapter. So, chapter 13, we've made it quite a distance in the book, and you guys have worked hard. And so we're coming down the home stretch. So let's see if we can finish well. We're going to take a couple lessons today and put them together as we really try to hit the high points of chapter 13. All right, so we're going to do lessons 13.1 and 13.2. 13.1 is the fundamental principle accounting. 13.2, permutations and combinations. That should ring familiar with you. Hopefully, we'll see when we get there. All right, 13.1, the fundamental principle accounting. Very, very easy, very simplistic principle. You won't have any trouble with this at all. Here's a situation. You've got A ways of a first choice and B ways for a second choice. Right? So many ways to do the first thing, so many ways to do the second thing. You know how you figure out how many possible ways? Just multiply them. Really easy, A times B. Piece of cake, no sweat. You can do that. Here's an example here in graphics. What do we got? We got two pairs of jeans, we got three shirts, and two pairs of shoes. So how many different combinations or how many different ways can these items be worn, assuming you're wearing one pair of pants, one shirt, and a pair of shoes, right? Well, it's real simple. You say, but wait a minute, the formula has two things and this is three. Oh, so what, right? The first is A is 2, and the second is B is 3, and the third's going to have to be C, and it's 2, right? Real easy. 2 times 3 is 6. 6 times 2 is 12, and there's 12 different ways. Hey, ladies, what if you purchase 5 skirts that all coordinate well with 8 blouses? So you have 5 skirts, and those 5 skirts coordinate very, very well with all 8 blouses that you just purchased. How many outfits do you get? Well, 5 times 8, you get 40 outfits. All right, hey, you can go over a month without wearing the same outfit. Isn't that awesome? All right, uh, real simple. The same concept, a little bit different aspect. Jed has 3 ways to get to Bill's house and 4 ways to get the Dairy King from there. How many different ways can Jed pick up Bill and get a shake? All right, and of course it would be strawberry. How many different ways? And this is a general permutation. You use the fundamental principle of counting, and it's real simple. 3 times 4 is 12, right? Pretty boring. Not a whole lot there. Okay, but something you should be aware of. Um, We can use a tree diagram to illustrate these, and so let me show you this, and then we're going to move on. But there's a tree diagram, and they can be illustrated. They can be used to illustrate the choices. So you start with, in this case, Jill is way down here, and you can see to the right, S1 is skirt number 1, and S sub 2 is skirt number 2. So we got 2 skirts, and remember, with each skirt, you've got some other possibilities. So here we got B of 1 is blouse 1, and B of 2 is blouse 3, and B of 3, or B of 2 is blouse 2, and B of 3 is blouse 3. All right, getting ahead of myself. Right, and then for skirt 2, you got the same situation. B of 1 is blouse 1, B of 2 is blouse 2, and B of 3 is blouse 3. And always, if you go to the end of the tree diagram, you'll see how many general permutations there are. And in this situation, there are 6. Okay? Tree diagram, not a big deal. You might run across one sometime. That's all it is. We're showing the first set of choices there, and then the second have to split off in each situation, right? No, not a big deal. All right. Here's something that should come back to your memory. We dealt with this. I know we dealt with it in pre-algebra. I'm almost positive we dealt with it in algebra 1 as well. Do you remember what the exclamation point stands for? What operation? All right, I hope you're thinking. Begins with an F. Factorial. 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 What is factorial? All right, we'll take the number times n minus 1. All right, look, n minus 1 is just a fancy way of saying the next lower number. Times n minus 2, which again is the next lower number, dot, 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 n minus 3, n minus 4, n minus 5, until you finally get down to the number 1. So in practical application, look at our example here. We got 5 factorial. So what in the world is 5 factorial? Hey, not a big deal, right? It's just simply 5 times 4 times 3 times 2 times 1. And, if you punch it out, it's going to be a little time consuming. Let's see, we can do this one in our head. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. And that would ultimately be 120, right? 5 times 4 times 3 times 2 times 1. You're multiplying times the next lowest number integer all the way down to 1. All right, but the reality is you have a calculator button. And your calculator button should look in one of these three ways. Either it'll just be the exclamation point for the operation of factorial, or it'll be an n factorial or an x factorial. You've got them. Sometimes it's underneath the statistics button, the PBR button, I think it is, PRB button, the PRB button. So if it's not on the face of your calculator, look for a PRB button, and it should be in the menu there. If not, look for a statistics menu. But you got to find it on your calculator. It's there. I guarantee you it's on your calculator. You got to find it. So if you need to, right now, pause the video and find the button. You need that button. All right, hopefully you're back. You found your button. Again, normally it's above one of the buttons or it's in those menus. You've got one. Again, if you don't have it, pause the video, find the button. All right, hopefully you're back now and you found the button for sure. 8 factorial, that's pretty simplistic. You punch it out in your calculator and it says 40,320. You'd never think it's that big of a number, but it is. That's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 40,320. That's a big number. Factorial. All right, that's important. It leads up to what we're going to do in lesson 2, which is right around the corner here, coming up in just a moment, right? So factorial. So what did we talk about so far in lesson 1? Hey, just a couple things. The fundamental principle of counting, also called a general permutation. Hey, just multiply A amount of ways of doing one thing, B of the other. You multiply them together. If there's 3 of them, just multiply all 3. 4 of them times 4. Tree diagram, just a way of illustrating that. And then factorial. All right, let's go on to lesson 13.2, permutations and combinations. All right, it is important that you can keep track of which is which. Now, when they're in their symbol form, it's very, very easy. But when it's a word problem, this is when you have to understand the concepts. All right, so you can see the form is showing right there, capital P. All right, permutation, that's not hard. If you flip the page, down the bottom, you'll see a combination, right, with a capital C. All right, I can figure that out. But what if it's a word problem? If it's a word problem, you have to determine whether or not the problem is a permutation or a combination, and you'll get a different answer depending upon whether it's a permutation or combination. So how do you know? All right, well, here's how you know. A permutation is an arrangement of a group of objects in a specific order. In a specific order. Let me try to illustrate this first before we go any farther. Let's suppose we had the numbers 1, 2, and 3. And we wanted to group them in 3 object groups. You want to use all 3. How many different ways can the numbers 1, 2, and 3 be listed? How many different orders? Okay, well, 1, 2, 3 is the first order. What if I leave the 1 in the front and I swap the 2 and the 3? Okay, there's a second way. All right, what if now I put the 2 in front and then we go 1, 3? All right, there's a third way. Let's keep the 2 in front. Let's swap the 3 and the 1. There's a fourth way. You got it now? All right, let's put the 3 in front and then we'll go 1, 2. And then we can leave the 3 in front. Let's swap the 1 and 2. And there's all the possibilities. There are 6 different permutations if we use the numbers 1, 2, 3 in 3 number groups. There are 6 different permutations that can take place with the numbers 1, 2, and 3 in 3 number groups. Okay? So that's the concept of a permutation. The order matters. When we get to combination, the order is not going to matter. You know how many different combinations you can get out of the numbers 1, 2, and 3 in three number groups? Just one, because the order doesn't matter. All right, so it's a whole different ball game. You always get more permutations than combinations. All right, so what about the notation? You can see a capital P for permutation. You got a couple subscripts. What does the N represent? What does the N represent? So this is the total number of objects. Total number of objects. That's the N. Always the total number you have available. Now the R is how many in each group. It's the number in each group. The number in each group. So what did I just do as an illustration? I did a permutation. We had a total of 3 objects, and we did it in 3 object groups. So we did the permutation 3, 3. And the answer is 6 for any permutation where you have 3 objects in 3 object groups. All right, let's see if we can understand a few aspects here. B, what if n equals r, like our example did? Then you know what? The permutation is simply take your red here and do n, and then I'm going to go green for my factorial button, or my factorial symbol. It's n factorial. So go back to our example here. This is really 3 factorial. And what is 3 factorial? 3 times 2 times 1. Isn't that 6? Oh, yeah. Hey, that works. That works. So I've got an example here, number 1. So what do we have here? We have a total of 7 objects, right? The red 7 tells you the number of objects. Take your green now. The green 7 says there are 7 objects. Let's see, there are 7 objects in 7 object groups, right? So we have 7 objects, and they're in groups of 7. So what does that mean? That means this thing is 7 factorial, and you can just punch that out on your calculator. So what is 7 factorial? Again, you found your factorial button, right? 5,040. You'd never think so. There are 5,040 different ways you can arrange 7 objects in a 7 object group. 5,040. That's what a permutation is. All right, so here, permutation 10, 10. How are you going to do a permutation like this? You're just going to say 10 factorial. Boom, right? Punch that out, and you're up to 3 million, right? 3,628,800 is 10 factorial. Well, of course, there's a formula for when n does not equal r, and this is the more common situation. Now, n's always going to be greater than r. You can't, if you only have 5 objects, how can you put them in a 7 object group? You can't. But you can take from 7 objects and have 5 object groups. So n's always got to be greater than r, and the formula is real simplistic. The top is n factorial, the total number of objects. The bottom is subtract the total number of objects from the object in each group and do its factorial. Pretty simplistic. That's easy to remember, and you really should remember the formula. It's easy to use, and it's not hard to remember, and so you really should. So let's do a couple permutations. So this is what's going to happen. You're going to have a problem like this. How many ways can you group 8 objects in 3 object groups? Well, that's a permutation. That's a permutation, so you have to know that. So I'm going to use the permutation symbol. How many total objects? 8. How many object groups? 3. So now run the formula. N factorial, 8 factorial, divided by n, 8, minus r, 3, and it's that amount factorial. So we end up with 8 factorial divided by 5 factorial, right? And you just punch it out. 8 factorial divided by 5 factorial, and the answer is 336. So you don't get as many ways because we're only doing 3 object groups. So you have 8 total objects. How many different 3 object groups can we make of 8 total objects? The answer is 336, permutation. All right, a couple more examples. So again, using the formula, I'm going to extend this up for my own benefit here. So again, what do we have? We have 26 factorial. And again, as you begin to understand, you're going to do 26 minus 10 on the bottom. All right, so much for color. All right, 26 minus 10. So you end up with 26 factorial divided by 16 factorial, right? 26 factorial. Go ahead and punch that out. It's going to be a big number because 26 factorial is big. 26 factorial divided by 10 factorial. Okay, and I just got a ginormous number. Let me do that one more time here. Divided by 16. Yeah. 26 factorial divided by 16 factorial. And the answer is 1.92. 1.9275. Who knows where to stop? Because look at this thing. It's times 10 to the 13th. To the 9th is billion. To the 12th is trillion. So this is like 19 trillion. Let me punch that one more time. It's bothering me. Make sure I punch everything correctly. All right, 26 factorial divided by 16 factorial equals, 1.9275 times 10 to the 13th. Let's suppose this. You're in a tournament, basketball, volleyball, whatever, all right? Baseball. There are 8 teams in the tournament. Fun tournament, 8 teams. How many different ways can they finish first through third? How many different ways? Well, it's a permutation. Total number of objects, 8. The objects are teams. How many are you going to put in each group? 3 of them, right? First through third. So it's a permutation 8, 3. Hey, we did that up above, and the answer is 336 different ways those 8 teams can finish. You'd never think it, would you? You go to an 8-team tournament, how many different ways can you finish? 336. I mean, that's kind of amazing. In my mind, that's pretty amazing. If you just had a 4-team tournament, how many different ways can they end up first through third? So the answer to this is really 4 factorial. And it's 24. You wouldn't even think that. There's 24 different ways 4 teams can finish first through third. That's amazing. All right, permutations. Well, look, here's the reality. Most calculators have a permutation button. And you say amen and amen. All right, you have a permutation button. Again, you got to locate it. A lot of times the PRB button is where you'll find it. Sometimes it's on the face of the calculator. Most times it's in a PRB. Some older calculators do not have a permutation button. Newer ones, again, in a PRB, maybe in a statistics menu. Again, pause the video and find your button because you definitely want to use the button. The button is so much easier. All right. So if you're back, I assume you found your button. And you're just going to punch it into your calculator. 35, permutation button, 15, and enter. And I got 4.247 times 10 to the 21st. You might say, how do we know where to round off? Look, this number's ginormous anyhow. Remember, 12 is trillion. So this thing is a billion trillions. So wherever you round off, you're cutting a whole lot out. All right, try number 2. Pause the video if you need to. 5. Usually it's the 51, then the permutation button, then the 4, and then enter. And I got 5,997,600. All right, let me show you one other alternate method that I think is kind of neat. I think this method is really, really kind of neat. All right, what you do is you start at whatever n is, okay? You start at n, and r tells you the number of factors. The number of factors. So let me illustrate that here with our example of permutation. We have 32 objects, and we're going to put them in 3 object groups. So I start at the n, the 32, and that's 1. It's one factor. I go to the next lower one times 31. There's the second, and I go to the next lower. There's the third, right? First, second, third, and that's it. Multiply that in your calculator. 32. Oh, how did I get 32 again? 32 times 31 times 30. We're counting down, right? For other. 32 times 31 times 30. And I got 29,760. Okay. Now, if you tried to use the formula, not the permutation button, sometimes your permutation button will do it, sometimes not, because this front number is so large. So some calculators won't let you use your permutation button on something like this because of 101. You definitely can't use the formula on something like this because normally your calculator won't allow you to do factorials greater than 99, and sometimes not even 99. Because you end up with an exponent that's more than 2 digits. Again, I don't know if you understood that, but you know, like 2.7 times 10 to the 99th, you'd go over the 99. So some calculators will still allow you to do the permutation, others will not. With the permutation button, you definitely can't use the factorial button, but you can use this alternate method. All right, so pause it and try to do it. Pause it and try to do it. All right, you're back. So hopefully you said, okay, I start at 101. I got to go 4 factors. There's my first, there's my second, there's my third, and there's my fourth. Hey, pretty simplistic. Again, you'd only want to use this method when the number of objects in each group is low. You punch that out. This is still, what, 97,990,200? Man, it gets up there quickly. 101 times 100 times 99 times 98 is 97,990,200. All right, permutations. Remember the key to permutations. They have a specific order. Okay? Do not forget that. They have a specific order. I don't know how much more I could emphasize this. They have a specific order, a specific order, a specific order. They have a specific order, right? It's a specific order. Permutation, specific order. All right, let's look at now a combination. So combinations, what are they? An arrangement of objects in no particular order. The order does not matter. No particular order. Doesn't matter the order that they're in, just how many groups you can make. Okay, what's the formula? N factorial divided by n minus r factorial. Hey, that's the permutation formula, isn't it? And all you have to do on the bottom is add one more r factorial. That's it. And now it becomes a combination. So some would like to say it this way. It's the permutation times r factorial. I'm sorry, times 1 over r factorial. Or probably should have said it this way. It's the permutation. Oops, let's get back to our pen here. It's the permutation divided by r factorial. That's a better way of saying it. Okay? Combination. Well, again, you have a button. Again, you might have a word problem. How many 4 object groups are possible if there is a total of 8 objects? Well, 4 object groups. We're just saying just a group of 4 objects. All right, this is a combination. So you got 8 total. Again, find your calculator button. If you found your permutation button, you should have seen your combination button. It's the easiest way to do the problem. Punch in 8, hit the combination button, punch in 4, and hopefully your calculator says 70, right? Combination 8, 4, 70. 70 different groups of 4 if you had 8 total objects. I always like to do this last example because I lived in Cleveland, Ohio for 13 years, and Ohio has the Pick 6 lottery. And there would be frenzies at times of people wanting to buy lottery tickets. And again, it's always, you know, the house always wins. It's money that you're really giving away. when you get involved. And even when you tend to win a little, you are getting gain for no benefit. There's a lot of aspects to that. And also, you're going to end up giving that money right back. Well, I wonder how many possible combinations. Here's how they did the Pick Six lottery. It was the numbers 1 through 50, so there are 50 objects, and they would pull out six numbers, and the order did not matter one bit. Didn't matter what order the six numbers were in, as long as you had the six numbers. Now the number couldn't be 111 because once they pulled the number 1 out, there was no other number 1 to come out, right? You have only 50 objects. Okay, so that's not a possibility. So the order did not matter. Well, this is just a 50 combination 6. Go ahead and punch it out in your calculator. And if you did it right, you got 15,890,700. There are 15,890,700 ways for those balls to come out of there in a group of 6. 15,890,000, almost 16 million ways. From what I understand, the probability of getting struck by lightning is like 1 in a million. You have a better chance of getting struck by lightning. 16 times better chance than hitting the lottery. All right, you probably know one or so people that's been struck by lightning. My brother-in-law, my sister's husband's brother. So again, my sister's brother-in-law, I should say, not my brother-in-law, won the lottery, and this was back 20 years ago for $5 million. That was a big deal. And of course, you thought that'd be the best thing for him, right? Well, if you have some time, I'll tell you the story and how it didn't turn out so well. Combinations. All right, combinations. Hey, remember, no specific order. That's the difference. How's the formula? Almost like the permutation formula with one little difference, and you should have a combination button. All right, that's it for today. Hope you have a great night. We'll work these homework problems in class tomorrow. All right, have a great night.